All right, this will be the start of chapter 11. So this one is labeled solutions, or at least this is what my notes say. I don't have my book with me. Hopefully that's right. And so this is kind of, I harped on this point a lot in the last chapter, but now we're going to really start mixing things together. So the idea of intermolecular forces are going to be equally important in this chapter as the last. In fact, I often mix these two chapters up in my head and think they're one, because the topics are so similar. You could essentially just write one giant chapter with all this stuff, but they decided to break it up, which works in your favor since I'm breaking up the exams by chapter. So you don't have one, monster test on all of it. We break it in half, which is convenient, I guess, for you guys as well. But this is really going to be what happens when we mix things together. So we talked a little bit in the last chapter about, whether mixing was favorable or not, or more favorable or less favorable. But now we're going to start talking about the effects of that mixing, what that means. And so the first thing we're going to talk about is ion interactions and how those drive solubility and dissociation. I touched on this a little bit in the last chapter. We don't really talk about ion-ion forces among our intermolecular forces in chapter 10, but they're there, and they are stronger than hydrogen bonding in general. And so that's why it takes a lot of waters to seduce a salt into dissolving, like I showed, because you have to have a lot of those ion-dipole interactions to overcome a single ion-ion interaction, if at all. It's not always possible. But we're going to really dial in now to the behavior of these ions and how they drive this process. And so the first thing I always like to open with is, a simple question. So, nothing, how could a question ever be complicated, right? And so I just ask, well, why is it that HCl, we dissolve in water, we get a strong acid, but HF, and this should be aqueous, by the way, this is also dissolved in water, is not a strong acid. Why is it a weak acid? And so to refresh your memory, if you're not super up on your chapter 4 stuff, strong acids completely dissociate. So all of my HCl's that I dissolve become H pluses and Cl minuses, but only some of my HFs that are dissolved become H pluses and F minuses. So there are some HFs floating around fully intact, whereas there are no fully intact HCl's. If it's dissolved, it has split apart. So why is that? Why do we get a strong acid or a weak acid? In fact, everything else in that column, HCl, HBr, HI, those are all strong acids. But for some reason, HF is a weaker acid. Like, what's going on there? I mean, you would think it would favor dissociation more, maybe, from like an electronegativity perspective. This is even more electronegative than chlorine. So it's really not going to want to hang around with its counter ion, you would think. But let's delve into it. So the first thing you want to remember is, we talked about this way back, refresh your memory, we were talking about bonding. But our ion-ion attractions are, let me make sure I got the equation right here, not equal, but proportional to our charges, Q1, Q2, divided by the distance of the ions. So we've got our charges and our distance between ions. All right. And so smaller ions with larger charges equals larger attraction. They're going to stick together more strongly. And if you look in figure 11.1, you get atomic and ionic radii. We see the following. So Cl minus and F minus. We're going to look at these anions. They both involve H pluses. That's a tie. Like, they're the same charge, they're the same ion. So the difference is the Cl minus and the F minus. Let's look there. Let's see what's going on. Well, they have the same charge. It's a -1 and a -1, so that's a tie. But their sizes are different. So if you look at your periodic table, you can tell that F minus will be smaller than Cl minus. And if you look at your table, 11.1, you can actually get numbers for it. And we're not actually going to calculate anything here, but this guy here, F minus, is 133 picometers, and chloride is 181. As you can see, I've clearly memorized these very important numbers. I'm not at all looking exactly at my notes and copying them down, but that should be what the table shows you. So this is smaller. That's the key difference. That is what drives this whole difference in behavior. It's a smaller ion. So what does that mean? Well, this means there's a stronger attraction between H plus and F minus. And stronger than H plus and Cl minus. And so there's not a strong enough attraction that they'll ever click back together. Water separates them and it keeps them that way. These, for the most part, actually stay as intact HFs when they're dissolved in water. Only a few of them fall apart, and they can click back together. And so it'll undergo what we call an equilibrium process. That's not for until the end of this class, the last chapter we cover, so we're not going to worry about that yet. But the stronger interactions, well, how does it drive dissociation? Well, stronger interactions equals less dissociation in H2O, and generally will also equal less solubility. So slash less solubility. So these are, the first situation. We're going to talk about dissolving crystalline solids next. These don't tend to stack into crystals. These tend to be gases that we dissolve in water, so they're a little bit different. But the idea holds, and I often have students in 221 from time to time ask me, why isn't HF a strong acid? If they look at their periodic table and they start studying the acids and they have to know the strong acids and the weak acids, a few here and there. This one always sticks out like a sore thumb. And so now you know why. It has to do with the fact that there is just a stronger attraction. It's harder for water to tear those ions apart. They're smaller, they stick together more firmly. Now, it's not impossible, but it's uncommon for them to fall apart in water. You can't get a solubility shell strong enough to counteract very effectively the attraction that they have. All right, so I'm going to clear the board here, and we're going to talk about dissolving some solid ionic compounds next. And this will be a little bit more what you lean on. This is kind of an introductory. There's a question I get a lot, I like to talk about it. So let me clear the board, talk about solids. Okay, so for ionic compounds that are stacking in a crystal structure, so salt crystals is what we're talking about. We're talking about solid ionic compounds now. So HCl, HF, they're gases. What about solids? Well, if the gases don't dissolve, in the case of HCl, it stays a gas, or it separates and dissolved. HF, it could be intact and dissolved, okay? That can't happen with these. Either they dissociate and dissolve, or they stay together and they sink to the bottom like a rock, like an insoluble salt. And so that's what we get. So if ion-ion attraction is strong, we start getting insoluble salts. So solubility goes down, 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 and eventually it essentially zeroes out. Again, we'll talk more about what essentially zero means in later chapters. But if we flip that on its head and we get weaker ion-ion attractions, well, that means we're getting greater water solubility because we're going to get easier dissociation. We're going to get more dissociation, which equals more solubility. That's what's going on. So in the case of these solid ionic compounds, the less strongly they stick together, the easier they're going to fall apart in water. And they have to fall apart in water or they're not dissolved. They just sink to the bottom. And so we can do a quick little example here. And so I can just ask a question like, which is more water soluble? So we got NaCl, we got MgS. These are both ionic compounds. We got a metal and a non-metal, metal and a non-metal. And you can look at your electronegativity tables and confirm that these are ionic compounds. But they follow the general trend. And so if we look at our periodic table, let's look at the charges of these ions. These are all going to be in the third row. These are all third row elements. So the chloride is going to be about the same size as sulfide. Na plus is going to be about the same size as Mg2 plus. There's not going to be a huge difference in sizes. So let's look at the charges. And we look at sodium, we see, oh, well, this becomes, let me get a different color marker. It's in the first row, so it has one valence electron to lose. That becomes a +1. Chlorine scoops up one electron. It's a -1. All right. We do the same thing with magnesium. It has 2 valence electrons to lose. That means it's a 2+. Sulfur can pick up 2 to fill out its valence shell, and we get a 2-. So we don't have to worry about orbitals or anything too crazy there. We can go back to good old valence theory, and it works for these charges. And so, you know, these are all, you know, about same size. You know, the size of, you know, Na plus, it's pretty close to Mg2 plus. And Cl minus is pretty close to S2 minus. And so if the difference isn't the size, it must be the charges. So the charges are very different. In fact, one of them is double the other. We got a +1 and a -1 and a +2 and a -2. Effectively, this +2 and -2 are going to have about 4 times the attraction because we've doubled both sides. You double it again, you get to 4 times. 4 times the attraction of the +1 and -1. So charges are greater on MgS. Well, that means that they're going to have stronger attraction, which equals less solubility. I asked which is more water soluble, so we can flip that on its head. So NaCl is more soluble in water because it has weaker attractions. It falls apart more easily. It's easier to pry the +1 from the -1 than it is to pry a +2 from a -2. Those are, you can think of like stronger magnets. Each magnet is twice as strong, 4 times the sticking force. It takes 4, you know, roughly. There's some wiggle room in there. You know, nothing's ever so simple, right? But essentially, you can think of it like it's about 4 times as much work to tear them apart. So you're not going to be able to do that as easily with water. And so that's going to be more likely to be an insoluble salt. But we could definitely say that this is a soluble salt. We've seen it dissolve. And by the way, I got another chapter. And it is a readily soluble salt. It has pretty weak attraction. Those are decent sized ions with a +1 and -1. That's the smallest charge you can get on an ion. So you can get weaker attraction. You can have something like potassium bromide or whatever. You just go down a row on the periodic table to get larger. But the idea holds. So again, which is more soluble? Well, which one just has weaker ion-ion attractions? And if they are strong enough, you get what's called an insoluble salt. All right, so that's kind of the introduction to this chapter. There's a lot of math headed your way, just a warning in the very next section. We're going to start really bringing some numbers into this. So right now it's kind of hand wavy. You know, there's this much attraction and the water either has enough to overcome it or not. At no point have I really written in any numbers. I wrote some, you know, what did I write? I wrote the size of some ions. That was it. And some charges, you know, +1, +2, -1, -2, that stuff. We're going to bring some actual math into it. So buckle up. Delta H showed up a little bit last chapter. It's about to show up big time in the next section here. In fact, I'll have to probably break the next section up into a couple videos because there's a couple key ideas and there's a lot of math to work through. So board space will be at a premium. All right, so you've been warned. So hang in there.